That's why yeah. I'm definitely in my they're not protected. So you didn't need any of this.
Okay, so today's class is about rigid body rotation. So, example would be a pendulum fixed about an axis and it rotates about the axis. It can rotate all the way around. So here is the first figure shows that's how a problem will be formulated. It will be an object which is pinned or hinged, and you're going to solve for either accelerations or forces. The first step is draw a free body diagram. Replace the pin joint with forces. In this case, since things are rotating about an axis, so you want to use ATAN or normal tangential coordinates. So I drew UT and UN. This is exactly the way I drew it for particles. UN always points towards the center of the circle. Well, imaginary circle as you rotate about point O. I put reaction forces at O, OT and ON in the directions of UT, UN. Once you have that, there are two ways of writing the equation. One is, well, as I said, there's F equals ma in the P direction, F equals ma in the N direction, and then the moment equation, because rigid bodies can rotate, particles do rotate, but we're not really concerned with the dynamics of rotation of particles, right? So that's the third equation comes because the rigid one. You could also replace that with this set. The first two equations remain unchanged. The third equation, however, is taking moments about point O, which is the reaction point. So we need to write MO equals IO alpha, where IO is the inertia about axis O. It's IG plus MR square comes from the parallax theorem. Okay. Now, why would you want to write well? First of all, either write this set or this set. Don't write both the sets, because this is not a new set of equations. This is the same set as that, because in a different way. Use one of them. The advantage of using this set of equations versus that one is when you take moments about point O, which is the pin joint, this moment O will not involve ON and OT. OT and ON will not feature in the equations because when you take moment about point O, those forces have zero momentum. And so if you do not want to solve for reaction forces, then you can actually use this equation to solve for alpha, and you don't have to do extra work. So just a judicious choice of points about which you take moments. You could take moments, by the way, about any point, and that's valid, but in this case, best to take moments about point either O or G, depending on the problem. So let's try to solve problems and see how these equations actually apply. The uniform slender rod has a mass m if it is released from rest when theta is 0 degrees. So if you see, theta is the angle made by the rod with the horizontal. So when theta is 0 degrees, the bar ABC is horizontal. Determine the magnitude of the reactive force exerted on it by pin B when theta is 90 degrees. So we need to find the reaction forces at B when theta is 90 degrees. So first step, well, we'll draw the free body diagram. And when drawing the free body diagram, even though you're asked to find reactive forces at 90 degrees, I highly recommend that you draw a free body diagram at a generic angle theta. Doesn't have to be, don't assume it to be 0 or 90 degrees. So let's draw it for a generic angle like so. B is this point. G is somewhere midway, right? It's exactly midway because it's a uniform rod. We can also write this distance. This distance is going to be 2/3 L minus L divided by 2. I think that's L divided by 6. See, if you sum those up, 3 divided by 12. That look right. So what's the sum? It's L by 6 plus L by 2. Yeah, that's right. So that's L divided by 6. I was just checking if the sum gives you 2/3 of L. Okay, so G is this point. Let's show the reaction forces, but before that, let's draw the coordinate axis. Okay, so as I said, the bar rotates about point B, which is the pin. And so when you're drawing the coordinate axis, you're supposed to draw the normal direction from center of mass, which is G, towards the pin joint. So it'll actually be like this, UT. UN, my bad. UN is always towards the center of the circle about which the rod is rotating. UT is at 90 degrees to UN in the direction in which the angle is, the bar is moving. So the bar is moving in this direction, so UT would be that direction. Okay, so now let's draw the reaction forces, and I'm just going to draw them. The direction is not important because if you assume the wrong direction, the math will tell us the right direction. So I'm just going to assume it's this way, PT, and randomly choose BN to be this way. And mg acts downwards. So that's my Freebody diagram. I can also see that if this is mg, this is the vertical direction, then this angle is going to be theta. Because this is theta, this will be 90 minus theta. So I can draw this as theta. Okay, I'm all set to write the equations of motion. Okay, since in this case I'm interested in Bn and Bt, right? You asked to find the magnitude of the reactive forces. You actually asked to find the forces and then take the sum of the squares and take the square root. So that is the unknown. We need to find that product. Okay, so if we can find Bt and Bn, we can find B, which is the magnitude. Okay, so for that I'll write the equations of motion. First we'll take equations in the n direction equals mass times acceleration in the n direction, which is rg times alpha. So the net force in the n direction is Bn with a positive sign because it's in the direction of n. Mg has two components. One component, the component which is in the n direction, is mg sine theta. In the way I've shown it, it's going to be pointing this way to your right. So it's going to be negative because it's in the negative un direction, equals mass times alpha times rg. Rg is the distance from G to the pivot point B, and we wrote that down as L divided by 6. Okay, that's equation 1. The second equation in the t direction is mass times omega square times rg. So all the forces in the t direction. So Bt acts in the negative ut direction. So negative Bt. Okay, mg has a component in the t direction. In fact, it will be this way. So that's mg cosine theta. And we can see that that component is in the ut direction, so positive sign, equals mass times omega square times L divided by 6. So Bn and Bt are unknowns. Mass is given, gravity is, we can assume it's given. Theta we can eventually sub in for theta 90 degrees. M is known, L is known, alpha is unknown, and so is omega square. So if we can find alpha and omega, we can solve for Bt and Bn and then get the magnitude. So the question is, how do you solve for alpha and omega? Okay, so that's where we use the third equation, which is the moment equation. Okay, now we have two choices for the third equation. We could take moment about G or moment about the pin joint, which is B. If we take moment about G, then Bt and Bn would appear in the equation, and that'll be, well, that's a valid way to solve the problem. We'll have three equations, three unknowns, and solve it. But an easier way is actually to use moment about B. If you do that, then Bt and Bn will not show in the equation. We'll actually be able to solve for alpha. And then we can sub that alpha in this equation, the first one. So let's try to do that. So moment about B equals inertia about B times alpha. So moment about B will have the only contribution towards the moment is mg. So mg times the, well, let's do it this way. We can take mg and resolve it in two ways. One is we can resolve it this direction, or we can resolve it in the perpendicular direction to bg. Now the component in the parallel direction, this one, is going to contribute, which is actually over here, this way, right? Let's put it here. That component is passing through B, so the effect of the moment due to that component is simply 0. So mg sine theta, which is this component, is going to give a 0 moment because it passes through B. This component, mg cosine theta, will have a contribution because it's at right angles to the rod. So the distance from G to B is the moment arm, which is L divided by 6. And if for a second you hold the bar at B and apply mg cosine theta, it has a tendency to turn the bar in the clockwise direction. So clockwise is negative, equals inertia about B. Okay, we know the inertia about G, and this is something which will be given to you. You don't have to memorize. It's ml squared divided by 2l. That's the inertia of a rod. So if you want to find IB, that's going to be Ig plus mass times the distance from B to G squared. So that distance is 6 squared. Right? Is that right? mLs. Okay, so if you simplify that, you should get, so when you simplify this and put it over here, you get ml squared divided by 9 times alpha, where Ig is given here. Okay, and now alpha, well, if for a second we assume alpha is counterclockwise, because that's a convention, then that alpha is positive. If you want to start off assuming alpha is clockwise, then you'll have to put a negative sign. So I'm just going to stick with a convention, which is we always assume unknowns to be positive. And then if they are not, then they'll come out from the math. So in this case, for example, when I put alpha as positive, it actually comes, if you put the values here, you get negative, which means that the rod is actually turning clockwise, not counterclockwise, which is what we expect it to do. Okay, so this helps us to solve for alpha. Solve alpha comes out to be 3 divided by, so negative 3 divided by 2 G divided by L cosine of theta. Okay, so we can take that alpha, plug it in this equation, first one, and solve for Bn, but we still need to find Bt. Now Bt has omega, so we need to find omega. Well, in this case we need to find omega at theta equals 90, but let's try to solve for omega. First let's try to find omega at a generic theta and then put theta equals 90 degrees. So if you want to find omega from alpha, what do? You need to integrate alpha because alpha is d omega dt. So if you try to do that, some kinematics. Okay, so we are trying to solve for omega. So d omega dt equals alpha. Now if you put alpha over there and try to solve for omega, then we will do that integral. So let's put this over here and take this dt to the right to integrate this. We just cannot integrate that because this is cosine theta. Theta itself is a function of time, right? Theta is the angle made by the rod with the horizontal is going to change the function of time. So we do not have an explicit expression for theta, so we will not be able to do that integral. So how do we get omega from there? So there's another way you can write the relation between alpha and the say that again. Here, this one. Yeah, I mean you got to generate that omega from an equation independent of that. So once I solve for omega, then I'll put it there. And this step is purely kinematics. You got to use. We've done this many times. There's another relation between omega and alpha. It's d omega d theta equals alpha, right? This is very similar to v dv ds equals a. So that is minus 3 by 2 g divided by L cosine theta. And so omega d omega equals minus 3 divided by 2 g divided by L cosine theta d theta. So we want to go from the rod starts off with is released from rest. So initial omega is 0. We want to find the omega when theta is 90 degrees. So initially theta is 0. And now when we put the upper limit, theta is, it's not 90 because our convention is counterclockwise is positive. The angle made by the rod with the horizontal is going to be minus 90 degrees. So this should be minus pi divided by 2.
Why can't you see that as done later?
You can do that too. I can do that too. If you want it, we'll do it that way. So minus 3 by 2 g divided by L. The integral of cosine is minus sine theta. So omega squared divided by 2 equals minus plus 3 divided by 2 g divided by L sine theta. Okay, so cosine is it positive or negative? It's positive, okay. That's right. Derivative of sine is positive, so it should be positive. So this should be negative, not positive. That's fine. So we've got 1, 2, 3, and 4. The last step is put 3, 4 in 1, 2, and also you're going to sub in the value for theta. Now theta is actually negative 90 and not positive 90, and the reason is because this is the 0 angle, horizontal. The bar is moving clockwise, not counterclockwise. So when the bar moves counterclockwise, it's negative 90. Because that's our convention, right? We assume alpha is positive, counterclockwise positive, clockwise negative. So that's why it's not minus 90. So we're going to put theta is minus 90 degrees and sub in for bt and bn in 1 and 2. If you do all that, you get bt equals 0. And bn equals 3 divided by 2 mg. And so the net force is going to be bn, right? 3 divided by 2 mg. Because bt is 0. Yeah.
Would the solution be different? Your equations for Fn and Ft are actually switched.
Did I switch?
Fn and omega squared r.
Really, I switched them?
Yeah,
Okay.
they were switched. So does that mean
No, yeah. So then what I did is incorrect, right? MAT acceleration in t direction is right. Yeah. So the answer I copied it from my solution, which is right. So
the solution would be right?
this, yeah, just my final answer is, well, my final answer is correct because I wrote it down in the right way. So Fn is m alpha rg, and this is m omega square rg. Is that right? No, I switched it again. I did the same thing. Yeah, good catch. So okay, anything else? So well, this is sort of a very common problem, and I would say you should just go through this and be able to do this, because there are many variants of the same question. Like, for example, if I take the pivot point, move it all the way to A, then that's a pendulum. Okay. Very valid, very useful, and there are a lot of things which are tested on this problem. There's how to find reaction forces, how to find alpha. In fact, let's do a problem where you just find alpha and see if you can sort of reproduce what I did. Okay, this problem is not as elaborate as the one I did, and should be fairly easy to do. At the instance shown, the uniform 30 kg slender rod has a counterclockwise angular velocity of 6. So you're given omega, which is 6 radians per second. Determine the tangential and normal components of the reaction at pin O on the rod and angular acceleration at this instant. Okay, so what I would recommend is just do this part. If you want to find alpha, you actually do not need to do the force equilibrium. You just need to take the moment equation about O. So if you do moment about O is I O times alpha, then you should be able to solve this. Yeah, that's the Freebody diagram. Take moments about Okay, in interest of time, I'm going to solve it. I'm not going to close the poll. I'm just going to solve it. You can change your answers if you want. So that's the Freebody diagram. Don't think I'm missing anything. So in this case, because I'm told to specifically find the normal and tangential component at this position when the rod is horizontal, I do not draw the Freebody diagram at a generic angle. But if you're asked to find the reaction forces or angular axis at a generic angle, or say 45, then you're better off drawing a Freebody diagram with the rod at a generic angle theta. Don't take 0 degrees and try to find the answer for 45. It won't generalize. So Freebody diagram done. Equations of motion. In this case, since I'm only solving for alpha, I'll do MO equals IO alpha. So the net moment at O is that due to capital M, which is counterclockwise. So counterclockwise is positive. Mg also has a moment. That's going to be mg times the distance from O to G, where this is G. So the distance is 0.15, and that moment is clockwise, as you can see, so negative. The inertia about O is mass times length square divided by 12. That's the inertia about G, plus the mass times the distance from O to G squared, so 0.15 squared. That's alpha. So the moment is 60 minus M is 30 kgs. 9.8 0.15 equals 30 times length is 0.9 square. Okay, instead of solving it, let me look at the answers. A bunch of people got 5.87. I think that, okay, I'm going to write 5.87 because so trying to solve it. Lots of people got that answer. So I would check this anyway. Okay, any questions on this? So this is just alpha, but you can also